As promised, here's the explanation for the Preparing Buffers lab. What I'm going to do is I'm going to go through the procedure, and I'm just going to read and do exactly what the procedure tells me to do. So, we've got goggles. You all were assigned 3 buffers that we were to produce. And the buffers that I am going to make, the group that the information that I am using had 4.95. The second buffer was 5.10. And then the last buffer was 3.95. Okay. So one of the things that I thought about was, well, what is the pH that I'm starting with? Because it tells me that we are starting with 100 milliliters of the weak acid. And we all had the same weak acid. We all had acetic acid. So if they tell me to start with 100 milliliters of a weak acid, that means I should already have some non-neutral pH, because it's not just water. So it's going to have a pH of its own. And that immediately got me thinking. Well, there were a couple of things. First of all, I thought about the fact that we had something similar like this, and I went back and I looked at our video notes, and it was actually exactly like what was in example 2 of our video notes for how we were to prepare a buffer. But I also thought that if I could visualize what was going on inside the beaker, then it would be very helpful. So this is a show me the chemistry moment, where we're going to look at what exactly is in the beaker. And since we are supposed to have acetic acid in here, it is a solution. We are going to have some water molecules just floating around, but we're also going to have our weak acid. There's acetic acid. And most of the acetic acid will be in this format, because it has a very small Ka, which means it has a very small extent to which it will dissociate in water. But some of those particles will dissociate, so we will have some acetate ions, very few, but we'll have some acetate ions. And we will have some of these hydrogens that were attached to the acetate that floated out and joined hydrogen ions to become hydronium. And then we'll have also lots of water in there as well. Right, so this is what we have to begin with. And so the first thing that I was curious about was, what is the pH of this? What is the pH if we have 100 milliliters of a 0.1 molar solution? And that was very easy to figure out. It wasn't something that I was required to do. They didn't tell us in our lab to do it, but I just needed to know where our starting point was. And so I have acetic acid, and I would have done pretty much everything for this lab with rice charts, because that's my comfort zone. That's what I like to use. The formula that's introduced in the lab is much easier. It is much quicker. We need to just go ahead and do that just because we do have a time test, but it helps for us to actually visualize what we're doing with that formula. So I have 0.1 molar. None of this to start with, minus X. Water is a pure liquid, which I didn't put in here, but so that's okay. Plus X, at equilibrium, this is going to be XX, 0.1 minus X. We said our Ka was 1.8 times 10 to the negative 5 molar, which is products over reactants. Products over reactants. When I solved for X, I got 0.00134 molar. So I plug that into my pH equals negative log of hydrogen ion concentration. And using that concentration, what I found was that the pH of my acetic acid was 2.87. So that gave me at least reassurance that I had a starting point. And I wasn't starting with water. I was going to be adding something to this solution, and I needed to make it up to 4.95 pH was the first goal. And this was what I had going on in that beaker. So now I've got a good starting point. Now I can go back and work that calculation. Okay. And what calculation am I doing? Well, I'm doing the one that they told me to do in the lab. So this is from page 1. And they gave me an example here. If you just go through the reading, they gave me an example of a weak acid and its conjugate base. So we can put that in here. It's a weak acid and its conjugate base, right there. Weak acid and its anion, which happens to be a conjugate base because it's negatively charged, it will attract a hydrogen ion. So here we go. Let's rearrange this equation here just to solve for the ratio of our acid to base. And again, this is something that they showed us how to do. I'm going to divide by Ka both sides. So I'm going to find whatever my ratio is of acid to base, and that's going to be determined by my hydrogen ion concentration, which I can get from pH, and then my Ka, which I'm already given because it is a constant. If my pH is 4.95, then my hydrogen ion concentration is 10 to the negative pH, and when I did that for 4.95, I got 1.12 times 10 to the negative 5. Okay, and that is molar. So I can plug that in. And when I did that, I got a ratio of acid to base that equaled 0.62 moles of acid for every 1 mole of base. That's what that ratio is telling me. And yes, these are concentrations, but since they're in the same solution, it's moles per liter, moles per liter. The liters would cancel out anyway, so I can simplify that to a ratio of just the moles. All right, so this is my target ratio, and I don't know how much base I'm going to have. That's one of the things I have to calculate. I have to figure out how much of the base do I add, but I do know how much of the acid I have, right? Because I had a 0.1 molar solution. It was 0.1 molar of the acetic acid, and they told me in my procedure that I had 100 milliliters of it. So if I'm going to figure out the number of moles that I have, that I actually have, I just multiply, right? Moles or molarity is moles per liter. If I convert this to liters, make that 0.1 liters times 0.1 molar, what I get is 0.01 moles of the acid. So at this point, all I need to do is set this up as an equality. I know that this is the ratio that I want to get to. I also know that this is what I actually have. What I'm trying to figure out then is how much of the base do I need to add? Keeping in mind that that base is going to be that sodium acetate that will give me my acetate ion to work with. All right? And at this point, it is just a little crisscross method here. And I worked out that math. We had 0.62 times X moles of base equals 0.01 moles of acid times 1 mole of base. Just yay, easy algebra. Yay, easy algebra. I want to know what X moles of base are, so I'm going to divide both sides by the 0.62 moles of acid. Right? So what I end up with is my moles of base, which were 0.0161 moles of that sodium acetate, C2H3O2. There we go. Knowing that this was a spectator, so really I'm adding this, but I need this whole formula because that's what I need to calculate the mass. This is the whole thing right here. The sodium acetate is what I'm measuring out from the bottle and weighing on the scale. So I need to figure out what that mass is. So what I do is I take my 0.0161 moles of sodium acetate. I need to find the molar mass. And I actually just looked on the bottle because a lot of those chemical bottles will have that information on there for you. 82 grams per mole was the molar mass. And so what that means is that I add 1.32 grams of sodium acetate to that bottle. So going back, all right, let's go back. So this is my magic number right here. This is my magic number of grams. And this is reasonable. I can weigh this. Some of us were getting really weird numbers because I don't know why. Because I was looking at 2 to 3 completely different problems with numbers in places and no units on some of y'all, and trying to figure out what it is that you were doing, and then trying to figure out what was wrong with it when you were all doing different things. Okay, so what we're adding, again, we're going to add the sodium acetate. I don't know why that's like that. We're going to be adding the sodium acetate, knowing that as we do so, the sodiums are going to be breaking apart. So as soon as we add that sodium acetate is going to break apart. The sodiums are going to be spectators because they are strong, so they will always dissociate. So we'll have acetate ions floating around. Let's see, let's have another one. If I have another one of these, I want to have them separate, so let me put these two different parts. So here, if I plunk that in, that's part of my solid, my sodium's going to go away. Not go away, it's still there, but we're not going to see it because it's in ion form. But we have this acetate ion here. What this acetate, negatively charged ion, is going to do is attract one of these hydronium's extra hydrogens, so we no longer have that hydronium anymore. Now we don't have this contributing to the pH. Now it's a neutral water molecule. And we are going to have that happen for every sodium acetate that we add. We're actually adding an acetate ion that could react with hydroniums and a spectator sodium that's just going to be there. But every acetate that we have could take away a hydrogen from those hydronium ions. And in that way, we're going to be reducing the number of hydronium ions, which is what will cause that pH to rise. Right? So that's how we're going to cause our change in pH. And that's how you calculate it. That's what's going on. That's show me the chemistry. That's the chemistry that's going on in the beaker. Right? I think that's all I need to go over for that. And so you're doing the exact same calculations. You're doing the exact same setup for the other problems. And I've got just a couple more minutes, so I'm going to go ahead and do one more. But you are doing the same setup. You have this formula here that you are working with. Exact same formula. It's going to be hydrogen ions over the Ka is equal to your acid over your base. And what's going to be different for each buffer is that your hydrogen ion concentration is different because that is based on your pH. So for example, on the next one where my pH was 5.10, I got a hydrogen ion concentration of 7.94 times 10 to the negative 6th. So you calculate that and see that you get that. I'm going to give you what I got for the mass of this, but if you follow the same procedure steps there, what I got was a mass of 1.32 grams of the sodium acetate. And the only thing you have to be careful of is on your third buffer, the one with the asterisk, the only thing that you really have to be careful of, it's the exact same setup, but you just need to be careful that the molar mass is the molar mass of sodium hydroxide. That's the only difference. Your base is a strong base, not the weak salt base. And that's it. That's all you had to do to calculate, and then you just made your solutions, and then I would check with a pH meter. And that is the lab.